All right, so we want to start mathematics. Okay. If you happen to go to CBU, you're going to find that this is called MA110. That is the course code. Um, I think other schools like UNZA, it's MA1100, something like that. Okay. Others they call it MAT110. Whatever it is, but it's the same thing. The content is almost the same. There may be a few differences. So let's look at sets. So I know you might probably familiar with this topic, but I want to assure you that I think a larger portion of this topic is something that you're not so familiar with. Okay, from your grade 10 and so on. So let's define a set. What's the definition? So we define a set as uh, a collection of objects, or you can say a collection of defined code elements. Okay, so it's a question of what defined objects called what called elements. Now, what are some of the characteristics? Okay, what are some of the characteristics of a set? Characteristics of a set. So now, one of the characteristics of a set is that it must be well defined. Okay, must be well defined. Now, what does it mean when we say it must be well defined? It should make it easy for you to identify and describe the set. Okay, let me give an example. Let's say we have set A, which is, let's say we have 5. Let's say we have Q, and then we also have, let's say, June. Then we have, let's say, Mary. Then we have, let's say, Zambia. Then let's say we have Cape Town. Okay, so let's say that is a set. You would say that that is a set of what? What would you just say that set is it's a set of? So this set does not make sense at all because you cannot tell what this set is. Okay, because you can see that there's a number, there's a letter, there's a month, there's a person, there's a country, there's a city. So it doesn't make sense at all. All right. So a set must be well defined in such a way that there must be well defined what? Objects or other elements must be well defined. You must be able to tell if this is a set of numbers, if this is a set of names of people, if it's a set of names of months, and so on and so forth, right? So that's how a set is supposed to be. So for example, let's say set B has, let's say, A, B, C, D, and E. Okay, let's say we end there. So we can see from there that set B, we can easily tell that set B is a set of what? Is a set of letters. Okay, A to what? To E. Okay, so this one is improper. We can't have a set like this. Then this one is proper. We can have a set like that. It's well defined. Okay, it's well defined. Are we okay so far? Are we clear? Are we able to see? Okay. Then let's move on and look at how to represent a set. So this is basically an introduction to set theory. Okay. So let's look at representing sets. Okay. So how do we represent sets. Okay, how do we represent sets? Now, we represent sets number one. Okay, we represent sets number one by describing. Okay, by what? Describing. Okay, so let's say, for example, let me try to use this. Let's say we have set A, which is, let's say 1, 2, 3, and 4. Okay, so we can say that in this case we can say that set is A is a set of numbers. Okay, is a set of natural numbers. Let's say of natural numbers. Of natural numbers less than what? 5. Okay, less than 5. So you can see that those numbers are natural numbers. We shall talk about sets of numbers, and they are all less than what? Less than 5. Okay, so that's how we can describe a set like that. Okay, then number 2, we also represent a set by listing. By what? Listing. Okay, the elements. So we can simply list the elements, like in this case, A is a set 1, 2, 3, and 4. Okay, like that. So we've listed the elements. Then number 3, another way we represent sets, we can use the Venn diagram. Now you're going to notice that in our discussion, or rather all right, so I was saying that the third way of representing sets is by using the Venn diagram. Okay, now like I mentioned, the Venn diagram, we're not going to look at it so much because it's something that you've been looking at almost all your life so far. So let's look at the fourth way of representing sets. Okay, what is the other way of representing sets? So the other way of representing sets, number 4, is by using what is called what? Using what is called set builder notation. Okay, so like in this case, for example, we can say that A is a set. Okay, we can say X such that when we write a straight line like that, it means such that sometimes we use the dots like that. Okay, which is more like a full column. But mostly we use a straight line, a vertical line. Okay, X such that we can say 1 is less or equal to X, which is less or equal to 4. Okay, and this X is a member of what? Natural numbers. Okay, X such that 1 is less or equal to what? Less or equal to X, which is less or equal to 4, and this X is a member of natural numbers. Okay, then the other way we can also represent the set bit notation of the same set. We can also say that A is going to be what? It's going to be X such that 1 is less than, 0 is less than X, which is, let's say, less than 5. Okay, and X is a member of what numbers? Okay, we can say it's a member of whole numbers or it's a member of integers. So there are many ways in terms of set notation in which we can still represent the same set. Then the other way of representing sets is by use of what is called the number line. The number line. Now this is going to be more useful when we start talking about what are called real numbers. Okay, this is going to be more useful when we start talking about real numbers. So please, let's keep that in mind. We're going to get to come back to we're going to come back to the number line when we start looking at what real numbers. Okay. So can you look at what are called equal sets and equivalent sets? Can you look at that? Okay. So let's look at equal and equivalent sets. Now, we say that we say that two sets A and B are equal. Okay, we say that two sets A and B are equal if and only if, okay, if and only if they have the exact they have the exact same elements. Okay, the exact same what elements. For example, let's say if A is 1, 2, 3, 4, okay, then B is, despite the order, no matter the order, okay, of course we're supposed to list them in the order of maybe in increasing order or decreasing order, but let me just try to write like this. Let's say 2, 4, okay, let's say then 1 and 3, like that. Okay, so we can see that these two sets A and B, they have the exact same elements. The elements are the exact same elements, right? So it means that A and B are equal sets. Okay, A and B are what? Are equal sets. Now, the other thing that we should mention, I'll mention this later on. The other thing that we should mention is that two sets A and B are equal, okay, are equal if and only if they are subsets. They are subsets of each other. Okay? If and only if they are what? Subsets of each other. Remember from your grade 12, is it grade 10 or grade 7? You'd say that a subset is a set within a set, right? A subset is a set within another set. So we can see that set A is going into set B, okay? All the elements that are contained in set A are also contained in what? Set B. And all the elements contained in set B are also contained in what? In set A. Okay? So with that in mind, it means that A is a subset of B and B is a subset of what? Of C. And because of that, it means that A and B are subsets of what? Each other. Okay? A and B are what? Subsets of each other. That is, A is a subset of B and B is a subset of what? A. Okay? So if you see that two sets are subsets of each other, then you should know that those two sets are what? Are equal. Then let's look at equivalent sets. Equivalent sets are sets that have the same number of elements, irrespective of the type of elements. So as long as the number of elements is the same, then it means that those sets are equivalent. So let's say, for example, A is, maybe let's say A, B, C, and D. Then the set B is, let's say, 7, 8, 9, and 10. Okay? So we can see that those two sets are having the same number of elements, right? So it means that those two sets are what? Are equivalent. Okay, those two sets are equivalent. Okay. Any problem? Any question? Is there any question before we proceed? Okay. So then let's look at subsets. So we say if all elements, found in set A are also found in set B, then we say that um, C, D, G, F, P, Q, X, Y, Z. Okay? So we can see that every element that is in A is also in B. Okay? Let's try to counter check that, right? So you can see that here we have G and there we have G. We have Q and we have Q there. We have Y. We also have Y there. We have Z and Z there. Okay? So every element in A is also in B. Okay? But not necessarily that every element in B is also in A. So in such a case, then we say that A is a subset of what? Of B. It is contained. It is a set within another set, which is in B. Okay? So a subset is a set within a set. If all elements found in set A are also found in set B, then we say that A is a subset of what? B. Okay? Are we okay so far? Are we clear? Any problem? Sometimes boring to finish up the video. Okay. So let's look at what is called the universal set. Okay, the universal set. So the universal set is a set containing all the elements and subsets. Okay, and subsets under discussion. Okay, under discussion. So all the elements and subsets that you're talking about, they belong to one large set called what? Called the universal set. Okay, called the universal set. Okay, then let's look at what is called the complement. Oh, by the way, let's say this is denoted by the letter E or the letter U. Okay, but most of the times we're going to be denoting the universal set within the letter E to avoid confusion with with union set, which we use almost the same symbol. Okay, so most of the times we're using E. Okay, so we're talking about, want to look at the complement. The complement set. Okay, the complement set. Now, when we say the word complement, okay, the word complement means to make complete, okay, to make complete or to finish, okay, or rather to, basically to make complete, right? If, let's say for example, if let's say we have something like this, and then we also have something like that, you can see that those are half circles. If we put them together, they're going to make a full circle. So this is the complement of that, and this is the complement of that, because when they're put together, they are completing each other. So what we're trying to say is that if you have a set, okay, if you have a set, you put it together with its complement, what you're going to get is probably the universal set is going to be complete. Okay, so the complement set, okay, is a set of elements that are outside a given set, but within the universal set. Okay, so what we're saying is that the complement set is a set of elements, okay, of elements outside a given set, but within the universal what? Set. Okay, within the universal set. So let's say let A be any set, then the complement of A is denoted as A with an apostrophe like that, okay, or A with a superscript C, okay, but most of the times we're going to be using this one, okay. So that is how we denote a complement of a set, okay. So now, how do we define it mathematically? We say that a complement is a set let's say X such that X is not a member of A. Okay? So in other words, we are saying that this complement set is simply a set of elements that are not members of A. Okay? A complement set is a set of elements that are not members of what? Of A, but within the universal what? Set. Okay? That is a complement of a set. Then let's look at what is called intersection. Okay? Intersection set. So when we say intersection, we are basically talking about the common ground, right? The common ground. So when we say intersection, we're talking about the set of elements that are found in both set A and set B, okay? If A and B are any two sets, okay, are any two sets, then the intersection of A and B, which is denoted as A intersection B, okay, is the set of elements found in both A and what? And B. Okay? The set of elements found in both A and B. So what are we saying? We're saying mathematically we say that A intersection B is equal to, okay, X such that X is a member of A and X is a member of B. Okay? So A is, that X is any element, okay, it can be any element. If it's a set of numbers, it can be a 1, okay, it can be a 2, it can be whatever number, or it can be whatever letter. But as long as it's found in what? In both sets A and B, then it qualifies to be part of the intersection set. Okay, let me give an example. On this one, I'm going to give an example. I should have given one also on a complement set. So let's say example 1. If the universal set is equal to let's say x such that 1 is less or equal to x, which is less than 10, okay, and x is a member of natural numbers, okay, and rather we say A is equal to 1, 2, 3, 4, 5, okay, and B is equal to, let's say B is equal to 2, 4, 6, 8. Okay, then find 1, let's say A complement, then 2, we find B complement, okay, then 3, we find A intersection B, okay. Let's try to find that very quickly. So what we're going to do is A complement, it simply means the elements that are outside A but within the universal set. So you can see that the universal set is having the elements 1, 2, 3, 4, 5, 6, 7, 8, and 9, because they should be less than 10, right? Less than 10. So let's cancel out those that are in set A. So you can see that 1 up to 5, they are within set A, okay? So therefore, A complement should be the set of elements, okay? Should be the set of elements 6, 7, 8, and 9. That is A complement. B complement, we're going to cancel out what? 2, 2, 4, 6, and what? 8. Okay? 2, 4, 6, and 8. So meaning that B complement is going to be 1, 3, 5,